So we're going to be taking a look at buffer 4 and doing some stuff with it. So I'm going to go to Cygwin. And have all of you used Cygwin before? Well, I'll still say it just for people who may be watching. So I'll just go like this to navigate, and then get the C drive, and it's in temp, and then lab 8. A very poor quality name. And we're going to do WinDebug, and that is in the command line, and it's buffer4.exe, and we're going to generate some input, or we will in a second. So I'm going to open another Cygwin here and use this to generate my input. So I can do python-c print and do, let's say 500 days, and of course I did that incorrectly. So this is just a simple command line application. We're just kind of revisiting some of the basic buffer overflow activity that we had done. Maybe learning some of the techniques of how we could make use of this inside a command line environment. So when we open it and it inserts a software breakpoint, the CC or int3, that's done with anything that you open inside of WinDebug, and we hit G to resume. And now it asks me for a password. So if I wanted to get to that, I can't do Control V, it doesn't work. So you can left click it and then do edit and then paste. There is no other command, you just have to do it that way. And I hit enter and I see, okay, it's crashed. It's EIP tried to go to 4141, etc., which was the ASCII for A's. But there's nothing there, and so we see the question marks, and so hence there is a crash. If we had supplied it with a valid address, then that would not have been the case. Of course, we want to narrow it down because we had 500 days. So we could try something more trivial, like let's just try 200 and see what that is. And I don't need to copy it. If I selected it, I've already copied it, so that's done. I like to do keyboard shortcuts, so I'll do Alt-D and then R, and that'll restart it. You can also do Control-Shift F5, but that's too much for me to remember and too many keys to push, so it's quick and easy for me to do it that way. I hit my G for go, and it looks like, so this is embarrassing, so let me get a different workspace here. So hit G for go, and now I can go in there and do my edit paste. Same thing, so we could reduce it even further, or alternatively, I guess this is probably what I should have done before, but this is still effective too. And of course, this is a review from what we have been doing. It's just trying to narrow it down there. So now it's in the B, so we made some progress there, and we could go back to our Cygwin and make some additional modifications. Maybe make that 50 and Now I'm just very quickly doing what I had to before, just restarting it. I thought I hit G, but apparently I did not. Still in the B's, so still need to narrow that down even further. So I can try 20, let's just do 20 and then 30. So by using the commands, it doesn't take very long. It can be very quick. And we're still in the B's there, which of course I knew because I know what the value is. Still in the, but look right here. So you might see the 4-2, but we also see 4-5-4-5. So that lets me know that I'm very, very close to it. So we could pinpoint really kind of exactly where it is because so 4-2 is going to be B's, and this is Little Indian, so it's going to be opposite. So I could do, I think if we do, let's try 9. Actually, well, maybe completely off, but let's see. For 5-4. So there's one more left that we need to account for. So let's try 8. That was what I had in my head, 108. But I guess let's go ahead and, I meant to do this earlier, but I guess I got sidetracked. You know, if you don't like interacting with all of that, you can also do a scripting process with Python. Python is very versatile. We talked about this last time here. So we were up here at 108. So we open this up. We create some standard, we create a variable, 108 A's, and then some B's and C's, and then our enter. So we need to have that enter. If we don't have that there, then it's not going to have the right result. Right here, it's seeking input, so we can attach our debugger. It's concatenating test and test2, and it's writing that out. So hopefully that should work for us. So let's see how we could, I'll just go ahead and close this out here. So I could go to the directory where it's located, which is over here. And I can do Python to invoke that script and test.py. I see attached debugger, so I can open my WinDbg. And I do file and then T for attach, which is up here. I guess you could do F6, but it's harder on a laptop. And I hit the end button, and that took me down to the bottom. And at the bottom, you're going to have the most recently open processes. So it makes it a little bit quicker to find what you're looking for, because it'll be down here somewhere, and it's right down there at the bottom. So you can be very fast as you do that. And so I can hit G for go. Actually, well, yeah, I can hit G for go. And then I'll attach debugger is looking for input, and we got a crash. So let's go back over here. And this one right here is set up so 108 A's and then 4 B's. So we captured EIP exactly. Just made use of a Python script to help us out a bit. So the point of all this is just really refreshing our memory in terms of using buffer overflow and seeing some of the things we can do with Python in terms of generating input or using a script like this. Another thing that we could have also done is, and I'm going to try to make this bigger, so I'm going to get the, let me restart this. And I'm going to open my workspace so that it looks a little bit better. There's something called load.pykd, PYD, and this is going to load a Mono Python script. And this is how it's set up in the iLab. So if you're not doing that, then you'll have to set it up on your own. And we'll talk more about that at a later time. But as I do that, then I can gain functionality that belongs to Mona. And part of that is this pattern offset, pattern create that I can do. So if I want to, and it's in alphabetical order, so I do PC or PO. So you do Pi, Mona, program counter size, let's say 1,000 of them. And it goes and generates those, and I could go and copy them and make sure I get all of them. So getting rid of any white space so that it's just only this. And so I have that, and I could take that and use that as my input. And so I set a breakpoint, so let's unbreakpoint it. Oops, didn't mean to do that. So I could hit edit paste with this input and see what happens. So I see this value here, which it's not that value. But I could check it anyway. And it doesn't find anything. It doesn't find it in there. So I could look at the stack and maybe, so in this case, it didn't really work out too well for us, but there can be other pattern creates and pattern offsets that Metasploit has them. You can go to an online website. So perhaps if there was a better value, then it would have worked for us. I think in this case, it just happened to be a valid address, and so maybe went to that valid address, and then from that location, it continued on until the program eventually reached the current access violation. So again, the point of that is maybe try a different pattern, and so a different pattern might be fruitful. So sometimes this can work and be useful, and sometimes it may not. So that's all cool and interesting, but we're going to move beyond that because this is a graduate level course, and I think we probably, a lot of us have some idea of buffer overflow, and maybe we've done it before, or maybe it's been a while, or maybe we've never done it. That's either way is fine, but we're going to get more advanced and oh, that looks terrible with all the light, but oh well. So we're learning about structured exception handler, and I know some people probably know quite a lot about it already. So what could you tell us about structured exception handler? What is it?
It's basically like if an exception is raised by the program, how it would handle it, basically, how it would continue after that.
Correct. So you could picture try catches. So SEH is a tool that, well, not a tool, but a way for programs to try to gracefully handle exception. So you could have exception handler, and you can go in there and create different ways of handling different types of errors so that it doesn't crash. The program continues on and it functions as the human being thinks that it should. As people who do exploits, we can take advantage of that and manipulate the SEH handler. So what is an exception? It's an event that is outside of the execution of the program, something that is not intended. Think of the try-catch. And so if this particular exception occurs, then we have code that may try to deal with it. It could be very elaborate, or it could just maybe gracefully ignore it and move on. It's really up to you how it's set up. So that's really what SEH implements. And when we do this, and we have an exception, then the handler will then go and search to try to find whatever is appropriate for that particular condition. Because you can have lots of different exceptions, and so you need to find a way to address whatever is actually specific to that location. And they can get very complicated and very convoluted. But as attackers, sometimes we can do a buffer overflow and we can overwrite part of the SEH. And if we can cause an exception, then that means that we can provide a series of instructions or addresses to allow us to then essentially take over control flow. All of that maybe sounds hard to grasp, but it'll become much more abundantly clear. So SEH, we can make use of the FS register. Do you two know what the FS register is?
I think I've dealt with a little bit in like reverse engineering.
Okay. So FS register indicates the threat information block. Some of you may know that because you can also use FS30 to get to the PEB. Well, FS0 also provides us with information. In this case, it provides us with information on the structured exception handler and also the next structured exception handler. So we can use that to view some of that information. So in terms of how we actually implement SEH, it's really a linked list structure. So we have the next is going to be the first one we see there. And that it points down over to the next location. And the H, the handler, will point to an address. The address will take you to a block of code that will address that particular exception. And it goes through them one by one. If it matches, then it goes to that. If not, it goes to the next one, so on and so forth. So it just simply walks the SEH chain until it can find the correct pointer. And there can be ways that we can overcome this, different techniques. So pop ret is going to be one technique that we can make use of. So a series of instructions such as pop EX, pop EBX, it doesn't matter what it's popping, and then a ret. And we'll see in another slide here how that works out. So how can we can trigger it? We can oftentimes it's done in conjunction with a buffer overflow. In this case, our goal here is to overwrite the SEH, not EIP. So we overwrite the NSEH, next SEH, as well as the SEH, and then cause an exception to occur. Oftentimes we may do that with a buffer overflow. Does every program utilize an SEH? No, that'd be great if that were the case. And there can be some additional protection mechanisms in place with SCH that we will talk about that can make things more complicated. But SCH is nice because we talked about the stat guard, the GS switch, which when you compile with Microsoft, it creates the cookies. So if you overwrite the cookie, then you're not going to be able to successfully do it like with the buffer overflow that we saw earlier today. It'll crash. But that one, the GS switch was turned off. So it was compiled GS dash or negative or minus. But if it had the GS, then it wouldn't have worked out that way. It would have caught it. It would have prevented that. But if there's a stat cookie in place, we can use SCH and overwrite that if it implements SCH, which it may or may not do. If it's a more sophisticated, larger program, then there's a good chance that it may do that. So this slide here provides probably a little bit better explanation in terms of everything that's going on. So we cause an exception, exploitation. We trigger it to go to the SCH handler. And then at this location, the SCH handler, then we can provide a gadget or an address that links to a pop ret. We don't care what it's popping, just as long as it has 2 pops followed by a ret. And then that will cause the NSCH to then go and execute the instructions that are located at NSCH. So you have 4 bytes, you can put instructions there, so it doesn't give you very much. So you could do something like EB06NZ or 9090, which is hex for small jump 6, and then 2 nops. And what that does is it just jumps over the SCH handler, and what would then follow there would then be your malicious payload, your shell code that you could execute. And that's if there weren't other things in play like data execution prevention. So that's what's going on there. In terms of why we would use the pop ret, this gets to a little bit into the weeds of it, a more technical explanation. So part of the SCH, we have an establisher frame that will be located at offset ESP plus 8 when the handler is called. That's a constant. That's always going to occur. And so at that point, the establisher frame points to NSCH. So if we have 2 pops, each pop is going to remove an address. An address is 4 bytes. So essentially we consume 4 bytes twice, or consume 8 bytes. So with those 8 bytes gone, then SCH then points to the stop of the stack. And thus when return hits, it will then execute the 4 bytes of instructions located in SCH. So, some of that may sound overly complicated. But you don't necessarily need to understand all the mechanics of how it works, just simply that it does work. And you don't have to necessarily always use pop ret. There can be other ways that you can bypass that. So you could have like add ESP 1000, and then for your NSCH you could have anything because it doesn't matter. And so I would just add to the stack. And so we need to know the exact number of bytes to overwrite both the SCH and NSCH. So in terms of how we fuzz that, we're looking at something a little bit different now. Different approaches that we could use. We could do our manual techniques, some of what we've done before. But in this case, we'll be looking at the SCH handler, and I'll show you how to do that inside of a WinDbg environment. So we can abuse the structured exception handler. We can overwrite those pointers. We can provide it with an address for pop.ret. And you don't really even need to know assembly. I mean, it could be Script Kiddie 101, no knowledge of assembly, and because it's not going into too much complexity at this stage. You just need to understand what pop.ret does. It's something that we use with our SEH overwrite. We place it in the SEH, and then the NSEH, which precedes it, then has our instructions to jump over that. So pretty simple, pretty basic. Don't need to have a deep knowledge at this point. I guess all this information is just repetitious. So FS0, you can dump the contents of the FS0 to view if an exception handler is registered, and so that should actually be DD, or it may work with D. I'm not sure, but I would probably do DD inside of WinDebug, and that'll dump the contents of that. So when an app has not begun, we will see just all Fs early on. That means it's at the end of the chain, and then after the application has begun, then we'll see more of it. Now, in terms of how we can make use of some of this in a WinDebug environment, we could send our payload. However we're sending the payload, whether it's file-based or we're doing something over a network, or it's local, we're doing input on a command line, however that may be, we send our payload and we're suspicious that maybe we want to see if we overrode it. We can do the bang ex chain command, and I'll display the exception handlers, and we can see, it'll allow us to see if we were successful in overriding SEH and NSEH. And if not, and if we were close, then we could refine it just using the same techniques that we did before, where we just narrow it down to the exact offsets. And you could try a pattern create type thing if you wanted to, although sometimes that could be problematic if by chance the pattern is a valid address. And so sometimes just those kind of wonky ASCII characters may be easier to use. So an example here of using EX chain. And this is after a crash has, well, it's not a crash, but an exception has occurred. We can go in there and do the bang EX chain. And I see that the 663 has overwritten SEH. So that's what that means there. And then the NSEH is then overwritten by 6262. So that's awesome. So now that we had narrowed that down, then we could go and find a pop.ret, or we could do some other mechanism like add ESP 1000 and then return. However we may wish to do that, we could see another case here of using an application that we'll be taking a look at later today. And so in this case, this is the pop.ret, the SEH that I have overwritten. And then the NSEH points to what we had supplied it. And I had said before, I said EB069090. It's just Little Indian. So that was a Big Indian way. This is the Little Indian. So it's just the NOPS and then the jump, EB6. So being familiar with the EX chain and using that in a WinDebug environment is going to be essential to knowing if you've compromised it and then refining it and developing it as part of the exploit process. So how do we look for the pop red instructions? There can be a number of different ways depending on tools that you utilize. If you know how to if you're familiar with certain tools, you'll know some other ways. But if you don't, that's fine. One way to find all of them quick and easy is to use the Mona Python script. How many of you have heard of Mona? Okay. So Mona Python script is developed by a guy out of, I think it's Belgium, Peter van Eckhout from the Corlan website about 10 or so years ago. And it searches for ROP gadgets and does some other general purpose exploit development type things. You can integrate it with WinDbg or Immunity, either one. So if you really like Immunity, you can set it up to work in Immunity if you like that. I don't think it's set up for x64 debug. It's possible maybe somebody ported it over, but I don't think he's really updated it in quite a while. But that's fine. It doesn't really need to be updated because it does what it does very well. So in any case, Mona will go through and it'll go and iterate through and search for any pop ret instructions. Some of these are intended instructions, some of them are unintended instructions. So when I say unintended instructions, how that works is you'll search for a C3, which is a return, and then you'll disassemble backwards and you'll check and see, is this a pop some register? Yes, it is. And then is the next one, pop some register? Yes, it is. And so now I found a pop ret, so I can save that and print that out to you. So essentially, that's what it's doing there. And with IA86 assembly or any Intel assembly, when you actually execute assembly on the CPU, you don't have to start the intended instructions because there is not what's called forced alignment. That means if I want to start in the middle of what the intended instruction is, I can do that. That's fine. It'll still work. But by doing that, starting at a different opcode, that completely changes what the assembly does, what it is. So some people think that the opcode correlates perfectly to the assembly mnemonics, and it really does. But if you start in the middle of something, then it's going to change it to something else. So by doing that, we can find unintended pop rets that may not have existed. Well, actually, that may be a poor example. So all of what I was saying was speaking more broadly, I guess, to the finding of ROP gadgets, which pop ret is a ROP gadget. But now that I think of it, I think that those particular instructions probably all are going to be pop ret no matter what. So, but in any case, we'll use that in a moment. So that's a way to do that. So with NSEH, then we want to put the opcodes to make a short jump, because that's what we're doing here with the shellcode. We're operating on opcodes. And so you could go. I can show you guys a website. May not be today, but at some point where you can just, if you're interested in a short jump of 6, then you could create that. And get the opcodes for that. But for SEH, you don't really need to worry about it too much because typically it's going to be a very short jump and it's going to be EB either way for short jump, and so whatever it is you're going to do, so whatever amount you're going to jump. Other considerations, all of this may sound great and wonderful. Okay, I can just do SEH. Unfortunately, there are mitigations that can make it so that it doesn't work out too well. We'll talk more about those at a later time. I don't want to overwhelm people, just because some of this type of material can be very difficult for some people to understand when they first encounter it. So we'll talk more about safe SEH and SE hop at a later time. There can be ways to overcome them, and the book does describe some of them, and some other websites do as well. So we'll go ahead and take a look. like 7 or 8 different. So in this case, we're going to do Easy Chat, which I know some people have already know all about. I have a trial here, so I have some extra messages that you guys may not have to deal with. I changed the port to 55, so if you have a script, you would want to reflect that. I guess I haven't provided you with scripts, but in class, but I will provide them online, but they should already be at 50. I should probably plug my laptop in. So this is our script, and so this is a chat server. So we are going to connect to it remotely over the wire. And I was going to show you guys this step, but the Wireshark on this VM was dated, and I tried to update it, but there are some issues, and so it's not actually functional at this moment. So what you would want to do, the first step here is when we're fuzzing for vulnerabilities, we're looking for a buffer overflow. And we're not really addressing the vulnerability aspect as much today. It's more the mechanics of the SEH and how that works. But ultimately, we would want to run Wireshark and to use this program as it is intended. And so we can then capture some of what goes up, some of the traffic, and so I can see things like this right here. And if I want to try to do an overflow, this may be a region of memory or region of the program that I may be trying to fuzz. So I have my malicious input here. It's going out there. It's doing a post. I have the malicious input there. Then I have the rest of this, which I don't think any of this actually matters, but and then just some more socket code to deal with that. I have the shell code right here. This goes and pops a calculator, so if we're successful, then that'll work out. I have my NSEH, I have the opcodes there, and then I have a spot here for my SEH pop ret. So first step would be simply to fuzz it. So I open it up, and now I have to attach it with the debugger. So let's go to WinDebug, and the same. I like to start very simple and get more and more complicated. Just go find Easy Chat, so we know how to do all of that stuff. And so now it's attached to it, and now I have a script. It imports everything I need. It takes the IP address, so it'll be local, and it'll send this input. So I don't know, what should we start as? Let's try 200. And then just do Python, and then stub3, and I need the address, of course. B is not defined. That was insane. I don't know why I have that there. I can go over here, and I have an exception. Before I didn't have an exception, and if I also go here, it's frozen. I can't do anything with it because it's paused, so I can deal with the exception. So I can do my Bang EX chain, and I have not overridden those, so I need to continue on. So I'll try, let's try 1,000. And just go and open ES again. It's running now. I can debug it. And then G for go. Let's see what we have here, what message. So now I have captured it, 6161, those are the A's, but there's a lot of A's, so I gotta narrow that down a little bit. So I could just do the file X to exit out of it and go back to my script. And what do we want to try, Hans? What do you think?
Well, we can start just having, like you said, we go on the 500 to get decently closer.
I didn't mean to do that, but. I'll make sure I saved it. I'm gonna do my EX chain. And still. Let's see what we get now. More 6-1s. That's depressing. Well, not too depressing, but. So sometimes you can launch things directly on the command line. Other times you want to attach to an active process, and that can make a big difference. So in this case, we're attaching to an active process. I'll set my input and check out my results. 4141, so we got to the uppercase A. My tabbing skills need to work apparently. So somewhere in this region. Do our easy chat, open that up, bypass that. Get our WinDebug. G for go. And launch it. Go check our results. Do our EX chain. 4.2. Ooh, we're very close. Actually, no, I misread that. It's so small. I thought I saw a 4.3 in there. But now we know that it's in this region. So as you can see, doing keyboard command shortcuts is going to make your life a lot easier. If you had to do this without that, it would take a lot longer. So anything you can do to automate your workflow is going to help you out. And you could probably, I don't know if you could automate it beyond this. Still in the bees, okay. Getting tired of those bees. Let's try 18. Do my EX chain. I can spell it. Okay, so I see the 4-2, so I know I'm very, very close there. And so let's see here. Not sure if I'm doing this right here, but we'll find out in a moment. I try not to think about it too hard. Just let the results guide me. Make sure I saved that. I did the opposite, so it was 18 and 18 plus 3, 21. Let's try that. Closed it. Sometimes those shortcuts don't work too well for you. Go ahead and try that again there. What am I doing wrong? We were close there, weren't we? Oh, 4-3, so let's just make this not overthink this too much. Actually, let's do this. Four two, 4-2, and 4-3. So maybe. So got the last 4 of these B's, the first 4 of these C's. So let's do it like this. Change that to and go ahead and launch our script, make sure I saved it. And hopefully, if I calculated correctly, 4443. So we were successful there. We did capture it exactly. So right here is going to be our NSCH. And then we need to get a pop ret. So right here is going to be our pop ret, and then our SCH is going to be right there. So I could go and when we input actual binary content, there's a special way we want to do that. We want to do it in Little Endian. So it's the opposite way. So if it was 9090 EB6, we're doing it the opposite. And so a D word, we have 4 bytes. So we do the first byte here, second byte here, third byte there, fourth byte. So I could get rid of that, and actually it'd be easier just to do it this way. Like that. So that's there. And now I need a pop ret. So let's go ahead and find a pop ret. So we need to make use of our Mona, so the load PYKD, PYD. And then and the commands are the same whether it's immunity or a Mona. It's just a little bit different in terms of setting it up. So we could look at all the options for Mona, and there is one for SEH. So we could go ahead and do that. So Mona SEH, and it'll go through the process that I described and generate all of them. And then outputs them to the log to the screen. But it also provides it as a file. So I could go over here and I see the file there. So that's the address for that. So I'll just take that and I'm just going to go here and paste that, and it opens it up for me. So I don't have to mess around with that. And so this is the output of Mona. And so we can see different DLLs, URL mon, kernel 32, MSVCRT DLL. And it lets us know if there's safe SEH, which is something we do need to watch out for. So we want something that is safe SEH false, unless we're using some other bypass. ASLR should be false. It should be predictable, because ASLR will randomize the base address. So if it changes every time, then it's going to be no good to us unless we have an ASLR bypass, which we don't. We don't have to worry about these other ones here at this point. So what this does is automatically it's going to find ones that are going to be safe SEH false, and it's going to be ASLR false. So these are good ones for us. It's not going to show us bad ones that are going to be useful to us, because it'll just waste our time. If you do have something like an ASLR bypass, then you would want to see those. If you could bypass, say, this DLL and MSW sock, then now you would care about those. But right now you don't care about them, so it doesn't show you those. So I'm looking for a pop ret. So I might just do so right there, pop ret, and then the 0 x08. What that means there is when it runs, it's going to take an additional 2 D words or 8 bytes off the stack. So for this one, I'm just going to avoid it, make it more simple. And this one would deal with 4. So I'm just going to do a pop ret. Actually, let's just do, no. Let's try ret. I don't want any of those 04s. So there we go. Here's one. It's an address. So I could take that. It's from SSLEA 32. It's a DLL for that the software. And I could hit the U to go unassemble there and see, is this really a pop-up ret? And I see PoppyBX ret. So that would work. So I can take that and then go over to my Sublime. And I want this to become, I still need to do that, this, but because of Little Indian, I'm going to have to do that same thing. And there's a way where we don't have to do this, and as we get into ROP, I'll show you, so you can just input it directly like this. But for right now, we'll just do it as if that did not exist. So I can go like that maybe so I don't get confused. So EX, AF, and then X, CD. Except, what is the problem here? What?
Null byte.
Yeah. So I got caught on that null byte. So null byte is a 0, so we don't want that. So I don't want any of those. So this one should work. So before I do that, I'm going to test it here just to make sure that, well, no, let's go ahead and do this. And then get rid of that ×4. And hopefully it should work now. Oh, hitting the wrong button. The moment of truth is fast approaching. Uh-oh. That is not what I anticipated. I must have copied the address down wrong. That's not a valid address. Sometimes when you're trying to talk and do things at the same time, then you don't necessarily think about simple little obvious things that you would catch otherwise. So that's completely not correct. Oh, it's only one that I messed up on, so. No need to retype the whole thing there. Make sure I saved it. And that looks correct there to me. I can grab it and do the U and check and see pop ret. So what do we think is going to happen? Well, we'll find out. I'm just going to go ahead and hit. So what it was trying to do there was it was trying to execute the 4 5s, the 4 3s. Those are valid instructions, so those execute. But then it gets to the 64s. Those are not valid instructions. So that's why we have the question mark there, and that's why we have the access violation, because it's trying to execute these ASCII characters as instructions, and it can do it for some of them, but it simply cannot do it for all of them. So what we would need to do is we need to have NOPs. So that's what we'll do. We'll use some NOPs, and we'll see how we can do that. So what we can do here is, again, it's going to these characters and it's trying to act upon them, interpreting these as instructions. And that runs into a problem when we get down to the was it the C, the 6-3 or 6-4, or I forget what it is. It may be the B's. In any case, the uppercase ones are fine because that's a 4, and that happens to be valid address. So it's probably the D here where it turns into, it starts with the 6, and it just doesn't happen to be a valid assembly instruction, that opcode, and so that's why it fails. So what we can do is we can have something called no-op, or NOP. So I'm going to say delete, goodbye, and we can do the NOP just like that, and let's do 350 of those. And so when it gets to those instructions, it'll do essentially nothing. Now if I wanted to have something like increment EAX, which was one of the things we saw earlier, I believe, or we could do that. It would just change the EAX value. It wouldn't really have a substantial impact on the end result. It would be functionally equivalent to a NOP. So we can go ahead and do that. So I'm going to save it. All right, we are ready to go in a second here. Let's go ahead and start our Python script, and we can check over here, see if everything appears to be in order. And indeed it does. We have our pop ret, and let's go ahead and I'm going to step into this. So there we go. It went to all of those NOPs, executed all the NOPs, and now it's taking us to our shell code. So I'm going to go ahead and hit G and let it go. And now let's try this again. Well, it's not showing here, but I do have calculators that are generating there. So we were successful. Now we would probably want to refine that a little bit so that the shellcode doesn't result in a multitude of calculators, but that's not really the purpose of what we're doing today. We're just trying to figure out how can I manipulate SEH. So I think we have a good idea in terms of having a starting point there. So right here we have our NSEH, and that takes us to our SEH. We use the pop ret to remove those 8 bytes, And then the instructional pointer goes to the NSEH, executes these instructions. So we have jump forward 60. And then I have 90 bytes to the shellcode. If I wanted to, I could have I'm sorry, I just lost in thought there. I was looking at the C's and the D there. I should have actually deleted those, but that's okay. It still worked for us. I got to our shellcode. I could have just deleted this and had the shellcode here, as long as we had enough bytes to cause the overflow. We may need to increase that stuff, maybe put 350 A's there, or something to that effect. So hopefully today's lecture was informative. All right, I'll talk to you next week.